In 1958, inside the massive Wright Aeronautical plant in Woodridge, New Jersey, the most complex piston engine in American history was already obsolete. The Boeing 707 had just entered commercial service, tearing across the sky with Pratt & Whitney turbine engines. Down below, Wright was still casting and machining the R-3350 duplex Cyclone, an 18-cylinder mechanical monster that had won a world war and powered the golden age of air travel. A decade earlier, the roar of a Wright radial meant American strength. The R-3350 delivered thousands of horsepower, powering fleets of Lockheed Constellations and heavy bombers. But overnight, the rules of aviation changed. Airlines did not want thousands of moving parts, heavy oil consumption, and endless maintenance overhauls. They wanted the clean, smooth thrust of a jet. Mechanics who had spent their lives mastering the grease and rhythm of radials suddenly inherited legacy equipment. The engine had not lost its power. It had simply lost the world that needed it. But the real story of Wright Aeronautical is not only the story of an engine line going quiet, it is the story of how an American empire pushed piston technology to its absolute breaking point, and what happened when the sky no longer needed that kind of power. Every week we tell the stories of American engines, factories, machines, and industrial names that once taught the country what power sounded like, and what happened when the market moved on. Subscribe if that history matters to you. The story begins not with nostalgia, but with a specific place in Paterson, New Jersey in 1919. In 1919, the name Wright already meant the invention of flight, but the men who built the first airplane had effectively left the manufacturing business. What remained was a corporate entity that set up shop in Paterson, New Jersey, a gritty industrial city previously known for weaving silk and casting heavy locomotive frames. Wright Aeronautical Corporation did not start as a giant. It began in the shadow of World War I, in a country that had not yet figured out what an airplane was actually for in peacetime. In the early 1920s, America did not have a commercial airline industry. It had the U.S. Airmail Service. The job was to move canvas bags of letters from New York to San Francisco. The pilots flew in open cockpits, navigating by following railroad tracks and bonfires lit in fields. But the real enemy was not the weather or the dark. The real enemy was the engine. The standard aviation power plant of the era was the Liberty L-12. It was a massive, water-cooled V-12 engine that produced strong power, but required a fragile ecosystem to keep it alive. A water-cooled engine meant the aircraft had to carry a radiator, a water pump, and a network of rubber hoses and metal clamps. For an airmail pilot flying over the Allegheny Mountains in winter, water froze. Over the deserts of the American West in summer, water boiled. The vibration of a wooden airframe constantly shook the plumbing. If a hose clamp vibrated loose, the coolant leaked out, the engine overheated, seized into a block of dead metal, and the pilot had to put the plane down in a dark field. America needed an engine that used the medium it operated in, air, to keep itself alive. The solution did not come entirely from Wright's internal engineering at first. It came from a man named Charles Lawrence, who had been obsessively developing an air-cooled radial engine. A radial engine, a piston aircraft engine with cylinders arranged in a circle around a central crankshaft, offered a mechanical elegance that water-cooled engines could not match. By pointing the cylinders outward like the spokes of a wheel, every single cylinder was exposed directly to the slipstream of the propeller. The engine did not need a radiator. It did not need coolant hoses. It cooled itself simply by moving forward through the sky. In 1923, pushed heavily by the U.S. Navy, which desperately wanted lighter, less complicated engines for its early aircraft carriers, Wright Aeronautical absorbed Lawrence's company. They took his rough designs, poured Wright's superior casting and machining capabilities into the blueprints, and engineered a machine that would rewrite the American expectation of flight. They called it the Wright J5 Whirlwind. Introduced in the mid-1920s, the J5 was a 9-cylinder, air-cooled radial engine. It had a displacement of 788 cubic inches, meaning the total volume swept by the pistons inside the 9 cylinders was massive compared to a standard automobile engine. Yet it was remarkably light. It produced 220 horsepower and sounded like a tearing sheet of canvas mixed with a deep, rhythmic hammering. To make the air-cooled concept work on a large scale, Wright engineers had to master metallurgy. The cylinder head, the upper part of the engine that helps seal the cylinders and contains the combustion passages, had to dissipate heat instantly. Wright cast the cylinder heads out of aluminum alloy and covered them in delicate, deeply machined cooling fins. These fins increased the surface area of the metal, allowing the rushing air to pull the heat away from the combustion chamber before the metal could melt. In the foundries of Patterson, pouring aluminum for aviation use was a dark art. Machinists who had spent their lives cutting heavy iron for railroad equipment had to learn the delicate tolerances of aerospace alloys. A single flaw in a casting meant a cylinder head could crack at 5,000 feet. The Wright factory floor became a place of obsessive measurement, where engine blocks were subjected to rigorous run-in tests before they ever saw an airframe. Out in the field, a new service network was being born. The Wright Aeronautical Service manuals, grease-stained books passed around the American hangar network, taught a generation of farm boys turned aircraft mechanics how to set the valve lash on a 9-cylinder radial. They learned the exact sound of a J5 running rich, the smell of aviation oil burning off a hot cylinder fin, and the ritual of manually pulling the propeller through before a cold start to clear oil from the bottom cylinders. The engine was building not just a company, but an entire American mechanical culture. The ultimate proof of this mechanical trust occurred in May 1927. A young, unknown airmail pilot named Charles Lindbergh was preparing to attempt a solo, non-stop flight from New York to Paris. When he commissioned a custom Ryan monoplane for the crossing, he had one absolute requirement. It had to be powered by a single Wright J5 Whirlwind. Lindbergh chose a single engine instead of a multi-engine layout because he believed in the math of the J5. He calculated that adding more engines only increased the statistical probability of a plumbing or mechanical failure. He trusted the Wright radial to run continuously for over 30 hours. When the Spirit of St. Louis lifted off a muddy runway in Long Island, New York, the J5 was pulling a massive overload of fuel. For 33 and a half hours, the 9 pistons hammered inside their cylinders. The crankshaft spun the propeller through rain, ice, and darkness over the Atlantic. The engine never coughed. It never overheated. It simply did what it was machined to do. Lindbergh's flight ignited an aviation boom in America. But in the boardrooms and factory floors in Patterson, New Jersey, the flight meant something far more specific. It meant the air-cooled radial engine had won. It was no longer an experimental alternative. It was the absolute baseline of modern aviation. The Whirlwind had proved that a radial engine could cross an ocean. The next question was whether a larger version could power an entire industry. The J5 Whirlwind was only the beginning. To power a true commercial aviation industry, Wright needed a machine that could carry more passengers, more freight, and heavier military payloads. In 1929, Wright Aeronautical merged with the Curtiss Aeroplane and Motor Company to form Curtiss-Wright, creating an aerospace manufacturing giant with the capital to build larger foundries and fund aggressive engineering. The result was the Wright Cyclone family, and its definitive masterpiece was the R-1820 Cyclone 9. Introduced in the early 1930s, the R-1820 was a massive 9-cylinder engine. The 1820 stood for its displacement, the total volume swept by the pistons inside the cylinders, measuring an immense 1,120 cubic inches. For context, a modern heavy-duty American pickup truck might have a displacement of 400 cubic inches. Wright was asking 9 massive pistons to hammer back and forth inside an air-cooled aluminum and steel block, producing up to 1,000 horsepower, and eventually up to 1,225 horsepower in later military variants. Building an engine of this scale required mastering a unique mechanical layout. In a standard automotive V8, every connecting rod, the part that links the piston to the crankshaft, attaches directly to the crankshaft along its length. But a radial engine, a piston aircraft engine with cylinders arranged in a circle around the central crankshaft, has only one single crank pin. To solve this, Wright engineers used a master rod assembly, one massive, heavily machined main connecting rod attached to the crankshaft, and the other 8 rods pinned directly into the sides of that master rod. This created a compact, short engine block that saved tremendous weight, but it also created a very specific culture on the American tarmac. Because the cylinders pointed outward in a full circle, the bottom cylinders hung upside down. When a Wright Cyclone sat idle overnight on a ramp in Chicago or Kansas City, aviation oil would seep past the piston rings and pool in the lower cylinder heads. If a pilot simply hit the starter button the next morning, the engine could suffer a hydraulic lock, the piston trying to compress incompressible oil, bending the connecting rod and destroying the engine instantly. To prevent this, American aviation developed a daily ritual. Before the ignition was ever turned on, mechanics or pilots had to walk up to the massive metal propeller and manually pull it through a few rotations by hand. This forced the pooled oil out of the open exhaust valves. Only then would the mechanic step back and the pilot engage the starter. The engine would cough, blow a thick cloud of blue smoke across the ramp, and settle into a deep, uneven, rattling idle that shook the entire airframe until the cylinders warmed up and expanded into their proper tolerances. The Cyclone did not just pull airplanes off the ground, it pulled them into higher, thinner air. To fly over the Rocky Mountains or avoid violent Midwestern thunderstorms, airplanes needed a supercharger, a mechanically driven compressor wheel that forces more air into the engine. Without it, a naturally aspirated engine would choke at high altitudes where oxygen is thin. Wright integrated a high-speed supercharger into the rear of the R-1820 block. As a Douglas DC-2 climbed out of Newark, New Jersey, the supercharger spun at thousands of revolutions per minute, feeding a densely packed mixture of fuel and air through the carburetor, a device that mixes fuel and air before it enters the engine, ensuring the engine maintained its horsepower at 10,000 feet. The engine reached Americans through a rapidly expanding service network. A Wright Cyclone was not a machine you ran until it broke. It operated on a strict schedule of preventative maintenance. The Wright service manuals, bound in heavy paper and soon stained with grease, dictated exact intervals for an overhaul. A major service process where an engine is taken completely apart, measured with micrometers, inspected for microscopic cracks, and rebuilt to factory operating standards. In hangars across the country, mechanics learned the specific metallurgy of Wright cylinders. They learned how to read spark plugs for signs of a failing fuel mixture, how to adjust valve clearances, and how to safety wire every critical nut and bolt so engine vibration would not shake the power plant apart in midair. This was a blue-collar mechanical force, thousands of young men who translated the high-level engineering of the Patterson factory into physical reliability on the flight line. The R-1820 became the backbone of both American commercial and military aviation. While its great rival, the Pratt & Whitney Wasp series, fought for dominance in the commercial transport market, the Wright Cyclone secured legendary contracts. The engine powered early airliners like the Douglas DC-2, helping to establish the very concept of a profitable passenger route. But the Cyclone's most famous application was strictly military. When the Boeing B-17 Flying Fortress took shape in the late 1930s, the U.S. Army Air Corps chose the Wright R-1820 to power it. Every single B-17 built for World War II carried 4 Wright Cyclones on its wings. During the war, the demand for the engine was so high that Curtiss Wright could not build them fast enough. The U.S. government had to contract automotive companies, including Studebaker, to build Wright R-1820s under license, turning Midwestern automotive assembly lines into aerospace foundries. By the early 1940s, the 9-cylinder Wright Cyclone was producing reliable mass-scale power. It had taught a generation of American mechanics how to maintain an aviation fleet, and it had proved that an air-cooled radial engine could sustain a global war effort. The Cyclone family had given American aviation its mechanical heartbeat. But as airplanes grew heavier and distances stretched farther, the market demanded a scale of power that would push the radial engine to the very edge of physical law. By 1942, the limits of the 9-cylinder radial engine had been reached. To lift heavier bombers and eventually transcontinental airliners, Curtiss Wright could not simply make the cylinders larger. The physical limits of metallurgy and cooling air dictated a different solution. They had to stack them. The result was the Wright R-3350 duplex Cyclone. It was a twin-row radial engine, meaning it had 2 banks of 9 cylinders, one positioned directly behind the other, spinning a single massive crankshaft. The displacement jumped to a staggering 350 cubic inches. Early military variants produced 2,200 horsepower. Later commercial versions would push well past 400 horsepower. To build an engine of this unprecedented density, Wright Aeronautical needed an industrial footprint that matched the machine. They constructed a sprawling, multi-million square foot factory in Woodridge, New Jersey. This was not a small machine shop. Woodridge became a self-contained aerospace city. It had its own foundries, its own heat-treating ovens, and endless rows of lathes where thousands of machinists turned raw steel and aluminum into high-tolerance engine blocks. Inside the test cells at Woodridge, the sound of an R-3350 running at full throttle was a physical force. It shook the concrete floors. It vibrated in the chests of the engineers. Inside the engine case, the mechanical ballet was almost incomprehensible. There were 18 massive pistons, 36 spark plugs, 36 valves, and thousands of gears, springs, and bearings all moving simultaneously in a space barely 5 feet across. The engine drank high-octane aviation fuel at a rate that required massive wing tanks, and it consumed heavy aviation oil by the gallon just to keep its internal friction from melting the block. In an America where an engine could decide whether a field was cut, a truck made its delivery, a boat left the dock, a generator carried a hospital through a storm, or a plane lifted from the runway, power was not an abstraction. It was iron, fuel, labor, heat, sound, repair, and trust. The R-3350 was the ultimate expression of that trust, but it was also a terrifying piece of engineering. Because the engine was air-cooled, the front row of cylinders received the direct blast of the slipstream, but the rear row sat directly in the hot aerodynamic shadow of the front row. Wright engineers had to design elaborate, tightly cowled metal baffles to force high-velocity air down through the deeply machined cooling fins of the rear cylinders. If the airflow was disrupted for even a few minutes, the engine would devour itself in its own heat. When the R-3350 was strapped to the wings of the Boeing B-29 Superfortress during World War II, it created a mechanical crisis. The bomber was rushed into combat service before the engine was fully matured. On the baking tarmac of airfields in the Pacific, the duplex Cyclone struggled to keep itself cool on the ground. If a pilot idled too long before takeoff, the rear row of cylinders would overheat. The magnesium engine components could ignite, and the wing could burn before the plane ever left the Earth. Yet, despite the wartime fires and the brutal maintenance schedule, Wright Aeronautical pushed through the engineering bottlenecks. Mechanics learned how to nurse the engine on the flight line. Engineers redesigned the cooling fins, upgraded the valve materials, and refined the fuel delivery systems. By the time the war ended, the R-3350 was no longer just a military weapon. It was a machine that had been tested in the most unforgiving environments on Earth, and it was ready to dominate the post-war sky. In the late 1940s and early 1950s, the American commercial airline industry exploded. Airlines like TWA, American, and Pan Am wanted to fly non-stop from New York to California and eventually across the Atlantic without refueling. To do this, they needed an engine that could deliver unprecedented speed and fuel economy. Curtiss Wright could not simply add more cylinders. The 18-cylinder block was already at the edge of physical reality. Instead, Wright engineers decided to capture the only energy the engine was wasting: the exhaust. The result was the Wright R-3350 turbo compound. It remains one of the most complex piston engines ever put into mass production. Wright attached 3 power recovery turbines, or PRTs, to the rear of the engine. A standard turbocharger uses exhaust gas to compress incoming air, but a PRT did something fundamentally different. It routed the white-hot, high-velocity exhaust gases, leaving the cylinders through 3 small turbine wheels. As the exhaust blasted through and spun these turbines at massive speeds, fluid couplings geared that rotational energy directly back into the main engine crankshaft. It was a mechanical masterpiece. The PRTs recovered energy that would have been lost to the atmosphere, feeding it back into the driveline to add up to 600 free horsepower without burning a single extra drop of aviation fuel. With a turbo compound system, the R-3350 pushed past 3,400 horsepower. It became the engine of choice for the ultimate generation of piston-powered airliners, the Lockheed Super Constellation and the Douglas DC-7. These were the aircraft that inaugurated non-stop transcontinental American air travel. To see a turbo compound constellation take off at night from Los Angeles International Airport was to witness the absolute zenith of the internal combustion engine. The PRTs blasted a continuous bright blue flame from the exhaust stacks, a visual signature of raw mechanical force tearing through the sky. Inside the cabin, passengers flew in pressurized, vibration-dampened comfort. But down on the tarmac, the engine was a terrifying beast to maintain. The sheer mechanical density of the turbo compound was staggering. The PRT spun at up to 19,000 revolutions per minute, bathed in exhaust gases that exceeded 1,500 degrees Fahrenheit. If a turbine blade failed under that intense heat and centrifugal stress, it could shatter, sending shrapnel slicing through the aluminum engine, cowling, or severing an oil line. In the maintenance hangars at Idlewild Airport in New York, mechanics developed a dark sense of humor about the engine's fragility. They sarcastically referred to the PRTs as parts recovery turbines. Every spark plug, every valve clearance, and every fluid coupling had to be perfectly calibrated. A single Wright R3350 now had 18 massive pistons, 2 supercharger speeds, 3 power recovery turbines, and thousands of highly stressed moving parts operating in a constant state of extreme heat and vibration. The foundries in Woodridge were casting the strongest aerospace alloys known to man, but it was barely enough to keep the engines from tearing themselves apart under continuous commercial load. The engines leaked oil so profusely that mechanics joked a Wright radial was only out of oil when it stopped dripping on the ramp. The Wright duplex cyclone had achieved what engineers once thought impossible. But that exact mechanical density, the thousands of moving parts required to create that kind of power, was about to become its ultimate trap. The fall of the Wright radial engine empire did not begin with a factory closure or bankruptcy. It began with a small, quiet crisis inside the maintenance logbooks of the American airline industry. By the mid-1950s, at airports like Idlewild in New York and Midway in Chicago, the ground crews servicing the Douglas DC-7 and the Lockheed Super Constellation were exhausted. The Wright R3350 turbo compound was a mechanical marvel, but it had pushed the internal combustion engine past the limits of practical maintenance. The first crack in the empire was not a lack of power. It was the sheer crushing cost of keeping that power reliable. An airplane only makes money for an airline when it is in the air. But the R3350 demanded constant attention on the ground. A 4-engine Super Constellation had 72 cylinders, 144 spark plugs, and 144 valves. Because the engines ran so hot and under such extreme cylinder pressure, spark plugs fouled constantly, valves burned. The power recovery turbines, the exhaust-driven wheels that gave the engine its massive horsepower, were subjected to such violent heat cycles that they required intense ongoing inspection to ensure a turbine blade did not shatter and slice through the engine cowling. In the hangars, mechanics were working around the clock. The overhaul intervals, the required time frame before an engine had to be removed, completely disassembled and rebuilt, were stubbornly short. The engine was burning oil at an astonishing rate, sometimes up to 2 gallons an hour per engine, requiring massive oil tanks just to complete a transcontinental flight. The math for airline executives began to shift. The engine still ran, and the passengers loved the speed, but the fleets were spending a fortune on parts, labor, and downtime. The American aviation industry had hit a mechanical wall. You could not simply build a larger piston engine. The R3350, with its 3,250 cubic inches of displacement and massive rotating mass, was already vibrating at the absolute threshold of what an airframe could withstand. Pistons stopping, reversing direction, and firing thousands of times a minute created violent reciprocating forces. To go faster, to fly higher, and to carry more passengers, aviation needed an engine that did not shake itself apart. The answer was already waiting on military tarmac. The turbine engine, an engine that uses spinning turbine stages and high-speed gas flow to produce power or thrust, rather than reciprocating pistons, fundamentally changed the rules of mechanical friction. A jet engine only had one primary moving system, the central spool that sucked air in, compressed it, mixed it with fuel, ignited it, and blew it out the back. There were no pistons. There were no valves to adjust. There was no massive connecting rod trying to punch through the side of an aluminum block. A turbine engine simply spun smoothly in one continuous direction. Curtiss Wright understood that the jet age was coming, but the massive corporation made a catastrophic strategic calculation. Developing a large-scale commercial jet engine from a blank sheet of paper required a staggering investment in research, metallurgy, and testing. The management at Curtiss Wright, led by President Roy Hurley, decided to prioritize immediate profits over long-term engineering gambles. Instead of designing a homegrown American turbine to dominate the new era, they chose to buy their way in. Curtiss Wright purchased licenses to build British jet engines designed by Armstrong Siddeley and Bristol. They brought the British designs to New Jersey, modified them for American manufacturing, and produced engines like the Wright J65. For a brief moment, the strategy seemed to work. The J-65 was a solid military turbojet. It powered American fighters and attack aircraft like the Republic F-84F Thunderstreak and the Douglas A-4 Skyhawk. But building a licensed military engine was not the same as commanding the future of American commercial air travel. While Wright was modifying British designs and trying to squeeze the last drops of horsepower out of the ER-3350 piston lines, their greatest American rival was taking a massive bet-the-company risk. Pratt & Whitney poured millions of dollars into developing the J57, a dual-compressor jet engine that offered unprecedented thrust and fuel efficiency. The market was waiting for a winner, and the verdict came down in 1955. Pan American World Airways placed a massive history-making order for the first generation of American commercial jetliners, the Boeing 707 and the Douglas DC-8. When the contracts were signed, the engines hanging off the swept wings of the new jets were not built by Curtiss Wright. They were built by Pratt & Whitney. The shock wave hit the Woodridge factory almost immediately. The airlines were no longer buying horsepower. They were buying utilization, simplicity, and turbine speed. And the mighty American piston engine had just run out of time. The shift was brutal and immediate. When the Boeing 707 and Douglas DC-8 entered service in the late 1950s, they did not just offer a new way to fly, they offered a fundamentally different economic reality for the American airline industry. A Pratt & Whitney turbine engine cost more upfront, but it could stay on the wing for thousands of hours without an overhaul. It burned jet fuel, which was cheaper than high-octane aviation gasoline. It did not foul spark plugs. It did not require a mechanic to manually pull the propeller through on a freezing morning in Chicago just to clear pooled oil from the bottom cylinders. For Curtiss Wright, the rapid adoption of the turbine engine was an industrial catastrophe. The massive Woodridge facility in New Jersey had been optimized for one specific task: machining, casting, and assembling the most complex piston engines on Earth. Woodridge was a city of lathes, heat-treating ovens, and engine test cells. But you could not simply retool a radial engine foundry to cast turbine blades overnight. The metallurgy, the tolerances, and the supply chains were entirely different. As the 1960s began, the major American airlines began aggressively retiring their piston fleets. The Lockheed Constellations and Douglas DC-7s, airplanes that were only a few years old and represented the absolute pinnacle of propeller-driven passenger aviation, were suddenly pushed out of the premier terminals. They were relegated to secondary routes and quickly to the cargo market. This was the quiet, grinding afterlife of the Wright R-3350. The engines that had once carried Hollywood executives across the continent were now flying late-night freight out of Miami, or hauling heavy machinery across the Alaskan wilderness. In this secondary market, the engines were pushed to the breaking point by operators who did not have the deep maintenance budgets of Pan Am or TWA. The power recovery turbines, the delicate exhaust-driven wheels that required constant factory-level calibration, were often run until they failed. Down on the tarmac, the service network fractured. The thousands of mechanics who had spent their careers mastering the Wright Cyclone family found themselves facing a new reality. The deep, rhythmic vibration of the radial engine was being replaced by the high-pitched whine of the jet age. Airlines no longer wanted mechanics who could nurse a temperamental 18-cylinder piston engine through a cross-country flight. They wanted technicians who could manage the clean, modular components of a gas turbine. As the years passed, the parts supply began to dry up. Curtiss Wright was no longer pouring new cylinder heads or forging new master rods at scale. To keep the aging cargo planes in the air, freight operators had to cannibalize dead engines. In aircraft boneyards across the American Southwest, mechanics stripped parts off abandoned constellations, salvaging carburetors, oil pumps, and cylinders just to build one working engine out of three dead ones. Curtiss Wright tried to pivot, but the momentum was gone. Without a flagship commercial turbine to compete with Pratt & Whitney or General Electric, the Wright engine empire was effectively locked out of the future it had helped create. To survive, the corporation did what many American industrial giants do when their primary product becomes obsolete. They diversified. They stopped trying to be the premier builder of aircraft engines and became a supplier of aerospace components. They built flight control actuators, high-tech metal extrusions, and industrial systems. The corporate entity survived. The balance sheet stabilized. But the mechanical identity that had started with a 9-cylinder whirlwind crossing the Atlantic was gone. The Woodridge plant, once the beating heart of American aviation manufacturing, slowly wound down its engine operations. The sprawling test cells, where the duplex cyclone once shook the concrete with thousands of horsepower, went quiet. The highly skilled machinists either retired or moved to other industries. The physical footprint of the factory was eventually repurposed and partially demolished. A massive industrial ghost town left behind by the speed of technological change. The Wright radial engine did not fail because it was poorly designed. It failed because it had succeeded so completely at pushing the internal combustion engine to its absolute physical limit that there was nowhere left to go. It had solved the problem of moving heavy loads through the sky, but it could not solve the problem of its own complexity. It was defeated by a machine with one moving part. The transition left a strange silence on the flight line. The engine still ran. The orders slowed. The airlines moved on. The parts became salvage. The mechanics retired. The factory lines stopped. The roaring sound faded. The badge remained. The sky it conquered belonged to someone else. But in the American sky, old iron takes a long time to fall completely quiet. Curtiss Wright did not go bankrupt when the last R-3350 duplex cyclone rolled off the assembly line. A massive industrial corporation rarely dies overnight. It simply changes what it sells. Curtiss Wright pivoted away from the grueling competition of primary propulsion. It became a highly diversified aerospace and industrial supplier, building flight control actuators, advanced metal coatings, and specialized mechanical components. The corporate entity survived the collapse of its piston empire and remains in business today, a quiet giant in the background of modern manufacturing. But the deep irony, the surprise footnote to an entire century of aviation, is that the company bearing the name of the Wright brothers, the very men who invented powered flight in America, surrendered its engine empire because it refused to invent the American commercial jet engine. They bought British designs, played it safe, protected their balance sheet, and watched Pratt & Whitney and General Electric conquer the global sky. The brand survived, but the identity of the Wright engine, the roaring heartbeat of American aviation, was lost. If you visit Woodridge, New Jersey today, the physical memory of that empire is mostly gone. The massive manufacturing footprint, where tens of thousands of men and women once cast aluminum cylinder heads, machined master rods, and heat-treated aerospace steel, was eventually sold off. Much of the site was repurposed or demolished to make way for commercial retail, transit centers, and residential development. There is no longer a deafening roar shaking the ground from the heavily reinforced test cells. The aerospace city that built the mechanical foundation of World War II and the golden age of transcontinental air travel has been replaced by the quiet, ordinary convenience of modern suburban geography. The industrial knowledge, the generational ability to cast the perfect cooling fin or balance an 18-cylinder crankshaft by hand, scattered and slowly aged out of the American workforce. But the engines themselves refuse to disappear completely. Old iron is stubborn. Across the United States, a dedicated preservation and enthusiast community keeps the Wright radial engine alive. At events like Wright Air Venture in Oshkosh, Wisconsin, or at regional air museums and restoration shops scattered across the Midwest and the Sun Belt, you can still hear the distinctive, tearing roar of a Wright cyclone. restored Boeing B-17 bombers, North American B-25 Mitchells, and the incredibly rare surviving B-29 superfortresses, like the famous warbirds Fifi and Doc, still rely on massive Wright radial engines to leave the runway. When a B-29 starts its 4R-3350s on a modern tarmac, a massive crowd always gathers, drawn by the thick clouds of blue oil smoke, the uneven, hammering idle, and the violent vibration that shakes the ground. This is not simply nostalgia. A running Wright R-3350 under a museum spotlight or strapped to a restored aluminum wing is not just a romantic reminder of the past. It is a physical, working argument about the absolute limits of engineering. It proves that there was a time when American industry believed the solution to needing more power was to simply add more moving parts, machine them to tighter tolerances, and force a blue-collar workforce to master the resulting chaos. To keep these flying relics in the air today, a small, highly specialized group of mechanics must operate exactly as their grandfathers did in the 1940s and 1950s. They still rely on heavy, oil-stained Curtiss Wright service manuals, books that dictate exactly how to safety wire a critical nut, how to read the burn pattern on an aviation spark plug, and how to manually pull a massive metal propeller through its rotation on a cold morning to clear pooled oil from the bottom cylinders before hitting the starter. Finding replacement parts requires scouring old salvage yards, trading with other museums, or custom machining new components from original blueprints, because the factory support network vanished decades ago. The existence of these engines today reminds us of the massive physical labor it took to make early commercial and military flight possible. The jet engine, the turbine that ultimately destroyed the Wright radial, democratized air travel because it was overwhelmingly reliable, clean, and required a fraction of the maintenance. But the modern jet engine is a sealed system, a quiet, hyper-efficient black box of physics that most passengers will never see inside or mechanically understand. The radial engine was deeply, unapologetically honest. You could see the push rods moving. You could see the deeply machined cooling fins. You could smell the burning aviation oil. You knew exactly how hard the machine was working to keep you in the air, and you knew how much human labor it took to keep it from tearing itself apart. America did not stop needing heavy lift, transcontinental speed, or global reach. It simply stopped needing the kind of mechanical complexity that required 18 pistons, 3 power recovery turbines, and gallons of oil to achieve it. The Wright radial engine empire did not fail because it built a bad machine. It reached the absolute ceiling of what an internal combustion piston engine could do, and then it was forced to step aside for the future. Somewhere in an American hangar tonight, the heavy steel doors are rolled shut. Sitting over a drip pan on a concrete floor is a massive, multi-row Wright radial engine. Its aluminum cooling fins scarred by heat, its push rod tubes coated in a thin film of aviation oil, waiting for a mechanic to turn the propeller by hand, a sleeping giant of cast iron and aluminum that still remembers how to make the ground shake. See you in the next one.